Well, good morning and welcome. It's our pleasure to be here this year. I think you'll see some very exciting different presenters today. We actually have 5 of us presenting. I'm going to start with an introduction to multithreading, kind of set the stage. My name's James Renders. I work at Intel up in Portland, Oregon. And then Jeff is going to talk about some work in Houdini. Erwin, will join us by the break, will talk about doing some simulation in OpenCL. George is going to talk about some work at Pixar, and then finishing up with Martin with some work at DreamWorks. What I really enjoy about the material that we have for you today, it's very practical, real-world experiences. So hopefully you'll gain a lot from the experiences of these folks. They're talking about work that's in production, what's worked and not worked in this very exciting area of taking advantage of scalable architectures, highly parallel devices. We did this tutorial one time before. The material today is quite a bit updated, and I'll make some comments as I go through it, some of the things that have changed, and I know each of the speakers have some additional experiences to share. But when we did this in Anaheim in 2013, we got the opportunity from a publisher to put an expanded version of this into a book. So we have a website. We can be contacted there. We have a Twitter account. We've got a website you can go. There is a book. And honestly, this is not an advertisement for the book. I want you to know it exists. The publisher asked, they're making it the book of the day in their booth. So if you are interested in looking at the book, you can drop by the publisher, and they're having some sort of a sale today on the book. We've gotten good compliments on it, but what it is an expanded version of the talk. I think you'll benefit from hearing us directly more than reading the book, but the book may have a little bit more details and depth. In any case, we do encourage you to contact us afterwards. We really enjoy following up. And anyways, let me get started. Do an introduction to multithreading. So I come at this, I've been doing parallel computing for about 3 decades, starting in college, and it was always a pretty esoteric topic. And I went off and hid in the worlds of supercomputers, but somewhere about 10 years ago, it became a much more fascinating topic for a very large audience. And I think it was in the embedded world and in graphics, it had already been getting hot by 10 years ago, but parallelism is a very intriguing topic, and we're still learning how to teach it, how to deal with it. And we'll be sharing a lot of examples of what we've been able to do so far. For me, the number one thing when I'm teaching parallel computing is this abstract concept of thinking parallel. And the fundamental reason that I try to emphasize this first is parallelism does not work well in an application if you jam it in as a last-minute thing. It's not something that bolts on very well, not if you're trying to get high performance. Really thinking about your application, its data, and so forth, and how you want to approach parallelism is incredibly important to do at sort of a holistic level. And this may seem obvious, but I've seen lots of examples of people getting very frustrated. They can't get their applications to speed up. They can't get their graphics to work faster because they haven't considered all the different aspects. So my objective in the next half hour or so is to walk through some of the ways I think about it, some of the things that I think are the most fundamental in terms of things you'll need to think about with parallelism, things like abstraction, vectorization, threading, tasking and the differences there. So hopefully I can explain that a little bit. It'll seem kind of high level and abstract, but it's things that have proven very well in experience as important. Now, why on earth parallelism? So somewhere about 10 years ago, clock rates on devices built in silicon stopped rising. We enjoyed for a long time a rapid increase in the clock rates of products. And this graph, I only plotted Intel processors on here, and the reason is I actually have the data on lots of other processors, but they may skew a little, but the effect is the same. And this is pretty dramatic because it's one architecture from 1971 to now, and it shows that the clock rate of products being introduced just suddenly stopped growing around 2004 or 2005. And it stayed that way. I got a lot of questions when this first happened. Is this just going to be a dream? It goes away. Won't Intel or AMD or somebody or NVIDIA invent a magical transistor, or maybe that'd be IBM that suddenly fixes all this? And what's been real interesting is over the last 10 years, some very magical things have happened, like moving to silicon dioxide gates and so on, that have allowed Moore's law to continue, but have not moved that stubborn limit on clock rate. And there's a lot of reasons for it. Power consumption's one, just intrinsically finding instruction level parallelism, and the other is that memory speeds simply don't go up. And the reality is we could build a device that's 4 or 5 or 6 gigahertz. We could build it, but no one would want to buy it. You would look at us and say, why on earth did you build this monstrosity? It's not worth the extra power consumption or heat. It doesn't give the performance. So while it's possible to build a faster device, it doesn't make any sense from a product standpoint or an engineering standpoint. But Moore's law continues. In fact, a month or two ago, there was a bit of a celebration of 50 years of Moore's law. So Gordon Moore is a really incredible guy, but he made a pretty simple observation back in the 60s, and that was that the number of transistors we can stick in a given area tends to rise about double about every 18 or 24 months. And this has really driven our whole industry in many, many different ways. And this continues. We must be getting nearer the end of Moore's law because each year goes by, but I've heard many, many explanations why Moore's law will end in a few years, and I've been hearing that for more than a decade. People keep finding ways to cheat death, and as far as I can tell, it's going to continue for a while. There are physical limits and so on, but Moore's law continues to give us more and more density, and the question is, what do we do with it? And primarily in the last 10 years, we've seen it used for parallelism. Now again, I drew graphs using just one architecture, Intel architecture. It's a long-lived architecture. It shows a trend. I can show the same trends for anyone else, and they look the same. In the last 10 years, parallelism's taken off. Take a look at the increased use of GPUs on die with processors. That's a form of parallelism. You see increased width, more cores. All of these things are instantiations. Whether you look at microprocessors or GPUs, the amount of parallelism getting dumped into the silicon has been rapidly on the rise for a simple reason, and that is we have more transistors year after year to utilize. And what's simpler than in a hardware perspective than duplicating your design out more and more fold. So we've increased core count, increased thread count, increased the width that data is operated on, increased the lines, the number of activities going on in GPUs, and also increased cache sizes, all to promote performance, but through parallelism. And this has an implication. Now, one of the projects I work on is the Intel Xeon Phi project. And I could draw the same graph for using Intel GPUs or NVIDIA GPUs or AMD GPUs. It's all the same. When you look at a highly parallel device, like a GPU or a Xeon Phi, we're relying on parallel programming. So this graph I've used in teaching because I'd have people show up to training. Oh, I want to run a parallel program on Xeon Phi. It's got 8 threads. I wonder how it's going to work. And I'd say, terrible. Because in the case of a Xeon Phi, you've got a device that can handle 244 threads. So if you show up with 8, it's just game over. Go use a processor. Don't bother with a GPU or a Xeon Phi if you can't give me more parallelism than that. You're sunk. Now the good news is, when I talk about this type of parallelism, even a simple for loop with independent iterations can supply the parallelism I'm talking about. So it's not like you have to go create 244 individual threads. If you've got a loop that's going to loop a million times, you've got plenty of parallelism potentially. But you have to have that. You have to find that. If you don't find it, you're sunk. The hardware is just sitting there screaming for a parallel program, but if you can't hit it, you won't get the performance. You're better off using a more versatile processor with a smaller number of threads for performance if you can't get a large number. So I keep saying threads, but I actually want to make a distinction. I want to distinguish the concept of task from threads. And there's a paper that I like by Edward Lee called The Problem with Threads. And I made a tiny URL for it. I even checked to see if this still worked after 3 years, but it's a tiny URL, threads yuck. If you want to read a paper that really slams the concepts of threads. But let me explain. A thread to me is when you look at a piece of hardware and you say, hey, it can do this many threads. And then I try to write my program to use that many threads, to map my code right onto it. That's a difficult task to do well. It's difficult to make it portable or performance portable. You're better off as a programmer if you can write in a little more abstract method using what I'd call task. A task is something you want to get done and that you're willing to have done in parallel with other tasks. But you're willing to let something else, that'd be the runtime of something like threading building blocks or OpenMP, you're willing to let it map onto the hardware. You're not trying to take total control. Now, total control is really a lovely thing if you want to study the architecture of the device you're targeting and perfectly write the code. You will probably get better performance than any other technique. But when the next generation hardware comes out, you're probably going to be rewriting your code. And so the first thing about parallel programming I'd suggest is understanding the role of abstraction and making sure you're picking the right abstraction. We are all smart enough to do anything once, so code, and tune. But the challenge is when you want to move it to another architecture. Is it performance? Is it portable, and is it performance portable? You'll do better if you can abstract it. So one of the things we've been learning with programming models is that we can make the programmer's job to identify parallelism, to bring it out, because compilers and things just suck, and they always will suck at finding parallelism. If it's hidden down in your code and you've written in a serial program, the likelihood a compiler will find it for you magically is it approaches 0. And it will stay that way forever. And I started my career as a compiler writer. I still identify with that, and it's just not a tractable problem, especially when you consider the programming languages that we're working in. So it's better if we have programmers program in a style that brings the parallelism out and then lets a runtime of some sort map those tasks onto threads. Threads being the units that try to map one-on-one to the hardware. So this way you could create thousands or tens of thousands of threads, or you could create the opportunity for millions of tasks. I'm sorry, see I switched words. Millions of tasks, and have that map onto how many ever threads your hardware happens to have, whether it's 8, 10, 244, or a few thousand. If you have enough tasks, they can be mapped onto threads at runtime. So, great reasons to be abstract in your programming. One is if you program too close to the hardware, you're going to impair your portability. And for some algorithms, that may be worthwhile, but think carefully about it. You'll see a range with the different speakers we have lined up today about their work in their tolerance for change. Some of them have libraries or larger selections of code that they don't want to really rewrite, and some of them may have a kernel that is worthwhile rewriting from platform to platform. And so there isn't one size fits all, but it's important to know that abstraction is available. And I'll give some specific examples of some of the things I consider to be more abstract. Another one is that nested parallelism is incredibly important. And this is happening, wasn't even on the radar 20 years ago. I'd say that anyone doing parallelism 20 years ago would just look at it as loop-based parallelism. I'm going to parallelize this loop. I'm talking about machines that may have 2- or 8-way parallelism. Those were the top of the universe, and that was great. And so some standards like OpenMP that came from that era really underestimated the need for nested parallelism. Nested parallelism means I may have started doing multiple tasks in parallel, but that some of those tasks will discover more opportunities to do stuff in parallel. And does your abstraction deal with that? And some abstractions do better than others, but my observation is that nested parallelism is really important. It's very difficult to write a program and break up the parallelism evenly, and so the concept of having unevenness and having that load balance to take advantage of the machine becomes very important, because you'll have, if you break up, if you're on an 8-core machine and you break up into 8 threads, those threads probably don't run even amounts of time. But if you break into a lot of tasks, you can do load balancing, and those tasks can discover more tasks. And then finally, vectorization. I'll talk a little about other parallelism methods, but vectorization. So I mentioned the programming languages we use today. So frankly, none of the programming languages, C, C++, Java, C#, Fortran, Python, Perl, Ruby, on and on and on, none of these languages were designed as parallel programming languages. Languages that were, including things like Haskell, are hardly mainstream. And our challenge is that we're trying to take what were designed as sequential programming languages and utilize them for parallelism. Now, some of the more modern ones, like maybe Java, if I can call that more modern than the others, have some concept of threads, but they really don't have a concept of efficient, high-performance parallelism, not built into the language. And that creates some challenges. But the fundamental question in all of these is, how can we add the right levels of abstraction? In fact, if we're going to add abstraction, I have a wish list. I want to be able to get good performance out of the hardware. I want to be productive at it. And I want to have portability, including performance portability. And there really is no perfect answer to this problem. The more abstract you go, you get portability and so forth, but you may get it at some cost. And the lower you go, the less portability, especially performance portability, you have, and you may need to rewrite your code for different machines. Now, taking a really broad swipe at this, I would say the higher level abstractions that are available to us are things like threading building blocks and OpenMP. You'll see a number of references to threading building blocks today by the speakers. And much lower level are OpenCL and CUDA. Now, I've had fun debates about OpenCL with folks. I don't usually speak very kindly of OpenCL because of the lack of performance, portability, and portability, but let's be clear, you can get great results with OpenCL, and we have some examples today as well. I'm saying don't use OpenCL and expect to get great portability and performance portability, but it does give you a level of control, that and CUDA, that's not present in the higher level abstractions. It's a trade-off. It's just a trade-off that's worth thinking about, not leaping into blindly. It's very disappointing to me to see people that have used, say, OpenCL or CUDA, and they're disappointed that they can't get the portability that they were wishing for. Equally problematic if somebody's using a higher level abstraction and they're trying to take advantage of detailed pieces of the hardware. There's a tension there, and there's just no perfect answer. But if we take a look at one language, if we take a look at C, C++, what's going on to try to fix parallelism here? And this is kind of a long-term project. There's a lot of different proposals. C++11 took some steps forward. C++, what is it, 17, I lose track, may do a few more things in C++ 21, if that's the number. There's a lot of debates going on in the C++ and the C standards committees about what to add. And they're being very conservative because they don't want to add something that then becomes a mistake later on. But we can take a look. One very successful project has been threading building blocks. So Intel's threading building blocks is an open source project. It turns 10 years old next year. It's very, very widely used, ported all over the place, many different operating systems and many different hardware architectures. It's been very, very successful. And I'll tell you a little bit about why I think it's been successful. One is the alternative to doing TBB was to use something like pthreads, or if you're on Windows, use Windows threads. And that means you explicitly go to the OS, you grab a thread, you run a task in it, you figure out how big the machine is, you create the threads, all of that. This example is an equivalent piece of code to do some very simple work. The things that I've circled is actually the algorithm. The thing that I X'd out is all the code to manage pthreads. And then the TBB code on the right, TBB just kind of hides the work. It manages the task. It lets you explicitly create them in a more dynamic. It figures out how wide the machine is and all of that. This is a very simple example. You can certainly write the code on the left. The challenge becomes, as machines change, that's the code that changes. The code that's in the circle, we actually know, using pthreads or TBB, kind of how to code up our algorithm. What we didn't know using pthreads is how to do that abstract enough. So TBB is actually written on top of pthreads and Windows threads. And so it's not magically doing anything you couldn't do yourself. It's just doing it for you. So with that in mind, what does TBB do for you? Well, at a very abstract level, TBB is oriented around handling tasks. So your job as a programmer is to specify tasks, and TBB's job is to map it onto the hardware. Now, you could envision a global queue. You put all the tasks on the queue, and any time a thread wants to do work, it grabs off the queue. That turns out to be a terrible idea because that queue becomes a global bottleneck. So there's some research at MIT in the mid-90s called Silk that pioneered the area of work stealing. And work stealing is a pretty simple concept. You have a distributed queue. Every core, if you will, has a queue on it. And we generally take work off that queue. The first thing we do is grab the youngest piece of work from my local queue. Nice locality, good cache behavior. The next thing I'll do is take away a task that I'm advertising. So mostly I have stuff that I will allow to be stolen and stuff I won't. It takes a little bit more work to take things out of my mailbox because I'm allowing other threads to potentially get them, so there is a lock to go through, but it's not highly contended. And then the other thing is, if I run out of work to do both the work I was keeping for myself and the work I was willing to let be stolen, then I will go and randomly steal from someone else. And so at the end of the work getting done, all the threads are running around looking for work, but that's not too much of a waste because the work is petering out. This allows an amazing amount of load balancing, and it's a very sophisticated set of algorithms written into TBB. And like I said, it's open source, so it's been, people have contributed improvements to it and so on, but it's all just in TBB, so it's not written into every application. So it can be improved and evolved while the programmer's code still stays looking the same. And it is very cache oriented. We think about work as having a big collection of work to be done, and we break it up into smaller and smaller pieces. So the leaves on this are the individual tasks to be done after it's been broken up. And work can be stolen. It's better if the work is stolen far away from us, meaning it probably isn't something we've worked on recently, so it's not in our cache. So the best place to steal from us is far away. The next best is a little bit closer. This turns out it works really well. This is a performance graph using TBB, and it shows that with a simple kernel that TBB will scale. And all that really means is TBB, with all the sophistication it has, work stealing stuff, doesn't get in the way of the scalability of our algorithms. That's all this graph says. It doesn't promise that your algorithm will scale, but what it says is that the overhead of all of this stuff I'm talking about is very, very low and can scale for many, many threads. In fact, this may be a little bit out of date in that I think we can scale to hundreds of threads now on some devices. So TBB is made up of a bunch of things. They all help with parallelism. And generic task, flow graph, task scheduler. There's a memory allocation. Highly encourage you to take a look at the memory allocator for TBB. A thread-aware memory allocator can improve your performance. If you're doing memory allocation and you don't have a thread-aware memory allocator, the first thing you should do is run out, grab TBB, and use its memory allocator. Now, I often say it can improve your performance 10 or 20% if you're doing a fair amount of memory. I've had people grab me and say I understated it, that it made their program run 4x. If you're doing a lot of memory allocation and deallocations and you're doing a threading in your program of some sort and you're not using a thread-aware memory allocator, you can be royally thrashing yourself. It's just a very good memory allocator. Eventually every memory allocator should be this good, but memory allocators for languages like C and C++ haven't comprehended parallelism, and that's a problem. Concurrent containers, STL in C++ is not thread safe. TBB provides a number of these. A lot of these are looked at by the standards and may eventually be adopted. Some of the things like locks and mutexes made it into C++ 11, and we'll see. So that's kind of a quick view of tasking. And, you know, if you want to use TBB is a great opportunity for a high level of parallelism. It's really pretty much available anywhere. It's open source, means it'll be around forever. It's got good degree of performance portability. It's a little annoying if you're not a C++ programmer. It's a template library, so C programmers tend to recoil from it. And I'm actually more a C programmer than a C++, but I like TBB, but I like that it mostly hides the templates, but I do need to have a C++ program to use it. There is a project from Intel called Silk Plus that explores how we can get this into C. Silk Plus is actually an open standard that's implemented in Intel and GCC compilers. A little bit of it's in C lang as well. it's really oriented towards exploring what could we do to bring this sort of goodness to the C language. And that's probably more of a standardization issue than it is likely that everyone will rush to Silk Plus today. But it's a good thing to explore if you're interested in looking at how TBB might be expressed in C. OpenMP, widely supported as well. Probably not as, it's much more a C and Fortran oriented set of extensions, and it's got some rough edges around composability. That it doesn't handle nested parallelism very well, which is generally turning out to be more and more important, especially outside of HPC. OpenCL, I said, very low level, not performance portable, but can give you strong controls over the hardware. And I just say, look, choice is good. These are all excellent choices to look at. Just understand the differences between them. Now I wanted to spend a little time and talk about vectorization because TBB and OpenMP tend to be very focused on tasking. OpenCL can do tasking and vectorization, but it can be challenging on a device that makes a difference between the two. So CPUs tend to make a difference between, they have handle threading and vectorization differently. They're distinct concepts. A little bit more flexibility. GPUs are a little less flexible and the concepts become blurred. And so vectorization becomes a very important topic in an application to understand how you're going to map onto any type of hardware, but on CPUs in particular, and that includes Xeon Phis, it's a topic worth looking at directly. So it's important for your application no matter where it's going to run. Now, if you've studied parallel programming, you may have heard people say there's task parallelism and there's data parallelism. That's sort of true. But at the end of the day, data parallelism is what really matters. If you're going to look for parallelism in your program, it needs to be in your data. And so if you're looking for 3 or 4 different things you can do in parallel task-wise, that's probably not the right approach. It's probably not as successful as looking for where am I processing a lot of data that I can divide up the processing of it. So this is Amdahl's versus Gustafson laws. Amdahl seemed to be very pessimistic about the ability to parallelize things, and I think the main reason that he was wrong is captured by a law called Gustafson's law, which really says that we should look at the scalability of machines by scaling up problems. And that's really the real world we live in. Problems become bigger, video becomes larger format, audio becomes larger format, big data happens, the parallelism's in the data. It was kind of interesting when we did this tutorial the first time and then we did the book. This is a slide that I use frequently when I'm giving talks. I noticed the distinct lack of talking about vectorization other than my introduction 2 years ago. There's a little bit more talk of it today. And the reason's pretty clear. You should parallelize your program first and then vectorize it second. The parallelization is more important to get performance if you have to pick one. The funny thing is, you really need to do both. And I'll pick on Xeon Phi because it's where processors are heading. They may not all be there yet, but it's where devices are heading. You can get 16x ideally from vectorization, but you can get 244x from threading. So it's pretty obvious that adding tasks or threads to your program will get you more performance. But the real kicker is the multiplication of this. So I can get 244x by threading. I can get 16x by vectorizing. If I do both of them, I can get 3,904x. Now, of course, you never get these ideal numbers, but the math is pretty compelling. And so what we see is go get your code running in parallel, but then go back and make sure you're taking advantage of vectorization because the multiplicative effects are amazing. So you could take a look at a simple program written in C like this. It just says, let's add a couple of vectors together and produce a vector. And the way that we would want a compiler to handle this is to pick up data elements one at a time, add them, and store them back. Well, if we've got vector instructions, we can pick up 4 at a time, for instance. Vector lengths may be different. We can pick up 4 at a time from each array, add 4 together in parallel, store back 4, and increment by 4. Each one of these instructions takes roughly the same amount of time, whether we're doing 1 thing at a time or 4 things at a time. So it's pretty obvious you'd like to do 4 things at a time. This is what we call vectorization. It's not rocket science when you look at it this way. It can be challenging to get your program to vectorize, but it's well worth the effort because you can see big advances in performance. A little problem. I showed you this simple loop. This loop's not legal to vectorize because in the C or C++ language, these parameters can be aliased. They could overlap, and picking them up 4 at a time may make the program behave differently. So here enters the headache of getting things to vectorize. You wrote a program in C like this that said do it 1 at a time, and the compiler is going to take you quite literally. You probably really didn't mean that. You said, oh, add this vector to that vector. But the compiler knows you could alias those parameters, and so it won't produce a vector version of this unless you help it. This is just an artifact that this language wasn't designed for parallelism. So there's a lot of different things we can do. We can hope that the compiler magically auto-vectorizes, or we can give it hints, or we could code differently. So a real quick tour of what we could do. The C language offers the word restrict. The word restrict says, I won't modify what this pointer points to any other way other than that pointer. And this magically gives the compiler a better chance at vectorizing, but it still doesn't tell it to vectorize it. Another thing we could do is tell the compiler ignore dependencies with this pragma IV depth, which is compiler writer language for ignore implied dependency, loop carried dependencies. I don't even want to try to teach when to use IV depth, and it still doesn't tell the compiler to vectorize. So along comes a pragma called SIMD that Intel introduced 5 or 6 years ago. It tells the compiler vectorize this. Just do it. Right or wrong, it may change the way the program behaves if I alias it, but I don't care. Now OpenMP added this into the language standard about 1.5 years ago, and it's been wildly successful. I actually thought it was the stupidest idea I ever saw, because I thought it changes the semantics of the language slightly, people will hurt themselves, and it turns out there was an awful lot of anger in the world over convincing compilers to vectorize. And I heard all sorts of words, phrases, some of them with expletives that I'll delete today, saying, dang it, compiler, just vectorize this thing. And that's what this pragma does. And I would highly encourage looking at this. Even if you're not using OpenMP for anything else, I think it's the best option for getting things to vectorize that exists today because it just tells the compiler, dang it, do it. Now, there's other ways and other methods, and there are some things including intrinsics. Intrinsics tend to be very tightly tied to the hardware. These intrinsics are very tied to a particular width. There are some people working on higher level libraries. I think Martin will talk about one that they're using at DreamWorks called SIMD Building Blocks. There's some other efforts like that saying, hey, can we take the concept of intrinsics but make them more generic so they're more portable? Maybe that'll take place. So I think a couple of things to look at are libraries like that or abstractions that look like intrinsics but are more portable, or look at the pragma SIMD that's in OpenMP and supported in a large number of compilers. And by the way, the pragma SIMD stuff applies to GPUs as well. It's lagging a little, but I know AMD's compilers support it for AMD GPUs. We support it for Intel GPUs and our compilers as well as our processors. And there's ongoing work in GCC to make it extend to different GPUs as well. I think the pragma SIMD has a lot a lot of good things going for it because it just tells the compiler, just parallelize this or just vectorize it. I really want you to. Now, I'm going to go back. The last thing I'll mention is data layout. To get something to vectorize, you're best off if the data is laid out in memory sequentially. Unfortunately, some of our applications will have structures and we'll have arrays of those. But what we want to do is access one member out of the structure repeatedly to do our vector operation. And so we're better off if we can arrange things as a bunch of arrays, or people often call it a structure of arrays instead of an array of structures. All it means is if you're going the order you're going to access the data in, try to get it sequentially in memory. Actually, what you want is an array of structures of arrays, but that's an advanced hour-long course for cache effects. But getting things laid out in memory is incredibly important for performance, and a difficult thing to do sometimes. But if your data is laid out non-optimally, it's going to affect your performance no matter what device you're trying to run in parallel. So, I want to close up and take a few questions as Jeff gets ready. I really want to emphasize, I think one of the things you'll see over and over again from all the presenters is that they've taken some time to think about where their parallelism is, not add it at the last minute. Think about how to do things in parallel. Reject algorithms that can't be expressed in parallel. Pay attention to memory layout. That's very important. Now, I'll do a few resource things, a few comments on places you can learn more in the form of books. I think some of the other speakers will talk about other resources. There's a lot of resources. Do a little Googling. But, of course, the book that we have from this course, there's also a book that's about 8 years old on threading building blocks. It's still an excellent introduction to TBB. The documentation that comes free with TBB is pretty darn good as well. I highly recommend looking at that or getting a copy of this book. I'm hoping to update this book next year. Some of the things you'll hear about in talks today, I hope to see in there some of the learnings about the sort of things people trip up on, because the book was put out about the time TBB came out. Now we've learned a lot about what works well, and we've added some features like task arenas you'll hear more about later that help with the abstraction. We've got a good book on teaching parallelism, structured parallel programming book that I was a co-author on. The website, parallelbook.com, has some good teaching materials, free for download, whether you're using the book or not. The University of Oregon, in particular, organized an entire class around it and made all of their teaching materials free, and there's a pointer to that on the website. If you're interested in teaching parallel programming, this is a really interesting topic, and I'm really glad to have that material available for free off the website. And then finally, there's a lot of books around examples of portable parallelism in the Xeon Phi world that I've been associated with on lotsofcores.com. And we've got tons of examples that are downloadable to learn from for free off that website as well. So with that, I'll say thanks, encourage you to contact us, and Jeff can get set up. I don't know if there are any questions before we move to Jeff.
So you mentioned teaching, and well, sometimes there are particular classes that you can give a student for entire parallel topic, parallel programming. I don't know if that's your experience in your teaching, but for a class, for example, for a student that you're just introducing them to threading or parallel, Do you have any insights? I do see students sometimes, struggle with threads, and I do agree tasks are a lot better, but sometimes the curriculum says teach them threads, because it's what people have been doing for a long time. So I would just listen to your insight about it.
So the way I think about teaching, you can teach parallelism two ways, and I'm not always sure which is the best. One way is to just say, hey, I'm going to teach a class on TBB, or on CUDA, or on OpenMP, or MPI, and I'm just going to show you how to do something. That has a lot of value. Just get your hands dirty and go. But when I teach a particular model, I may be missing the opportunity to teach more generic concepts of parallelism. Now, I'd much rather teach a class on CUDA than Java, for instance. That's a personal bias. I want you to understand that there's some parallelism in the hardware and how you might use it. The other approach that we took with structured parallel programming is the book is to teach what I call patterns. Although, if you know much about the study of parallel patterns, you might know that some people get really into parallel patterns and they enumerate thousands of patterns. It's very confusing, at least to me. What we did is focus on patterns that work. So for instance, we teach about stencils. If you don't know what a stencil operation is, and the fact that many, many people have figured out how to make that run in parallel, that's probably a mistake if you call yourself a parallel programmer, or if you don't know what a map or a reduce operation is. So we took the approach of teaching those generic things and emphasizing them because we know how to make those run in parallel. So if your program even gets close to a stencil operation, you should probably turn it into a stencil operation because we know how to make that run in parallel. A lot of teaching computer science is like that. If you can show what people have done before that you might imitate, it's really helpful. So I actually prefer to teach parallel programming that way. It's a little more esoteric. And then for each example, teach it in something like OpenMP or TBB, but emphasize the parallel patterns that work, and then let people build on that knowledge. It's a good question. It's a tough question. And that's why we did the Structured Parallel Programming book. I try to take that approach of teaching parallel programming when I can. All right, one more question.
Great talk. I'm very new to TBB, but I was wondering, is there any plan for future to extend concurrent containers? Because they are very limited and there are so many missing functionality when you compare to a standard containers. So.
Yeah, it's a great question. So the question is there any, TBB has a few containers that are highly concurrent, like hash tables and queues, but really didn't do things. The most common question I get is, why isn't there a concurrent list? And the short answer is because we don't know how to make a concurrent list perform well. But if you have ideas about that, the TBB team would love to add it or have someone contribute it. There may be some types of data structures that don't work well in a parallel world, and lists are one of them. Queues work better. And so there aren't any plans I know of right now to extend containers in TBB, but it is an open source project, so if someone comes up with a great idea, we're all ears. And the TBB team, in my experience at Intel, does a really good job of taking feedback if there's ideas on how to solve a problem. But the containers is a tough question, and one that gets debated at the standards committee as well. Good question.